And here is on a slide that I skipped yesterday, where when we were talking about the geomechanics part, the geomechanics component of the model. But I'm going to go over this slide very quickly here, because that is kind of the basis of what we're going to do with the spreadsheet. So here we discussed the Mohr circles, and here are different fracture orientations, and here's the orientation of the maximum horizontal stress. And there are this is also taken from the book of Mark Sobak, 2007. He indicated here 3 different colors for fractures. There are fractures that are the blue fractures are basically subparallel to the maximum horizontal stress. They have the green fractures that tend to be perpendicular or pseudo-perpendicular to the quasi-perpendicular to the maximum horizontal stress. And then these are kind of purple fractures that they have a certain angle, maybe around 30, 25, 35. Okay, so when you plot these fractures in the Mohr circle, these are the ones that are close to perpendicular. Remember, we said yesterday that totally perpendicular will be right here, 0 shear stress. Here are the ones that are close to parallel. Remember, totally parallel, as we discussed yesterday, is right here, 0 shear stress. And then this is the one at around 30, around a certain angle. Okay, so then remember an important parameter here is the pore pressure. Okay, the pore pressure will tell you where the center of the Mohr circle is, and then so that if you have fractures that are closed, meaning that they are below the friction line, they will plot in this area. But then as you start increasing the pore pressure, the Mohr circle will start moving to the left, and eventually some of these points, as we explained yesterday, they will cross the friction line, and then they become more prone to be open. So if they were closed, they become more prone to be open. Or if a fault was kind of quiet, it can get reactivated and it can create seismicity. Okay, you increase the pore pressure only up to a certain limit. You cannot increase the pore pressure more than the minimum horizontal stress or close to that. Maybe you can put it a little bit more, but not much more. So this is what is called the hydrofrac limit. This is a physical limit. So what we're going to be doing with the spreadsheet today is basically analyzing this kind of effect. And in particular, what the spreadsheet does is that it calculates this number, or the distance, or how much pore pressure you need to take any orientation to the friction line. So something, for instance, this fracture here that is originally closed, what the spreadsheet will do is that it will tell you, okay, you will need to add this additional or increase the pore pressure by this amount from here to here in order to make that fracture, to reactivate that fracture. Okay, that number is calculated in this way. That's the equation that the spreadsheet solves for. The pore pressure, that is a combination of the friction coefficient, the normal stresses, the shear stresses, and divided by the friction coefficient. If this number, as we said yesterday, is less than 0, means that you cross the friction line, then the fracture is reactivated. If this number is greater than 0, means that you are still below the friction line, and then that fracture is closed. Okay, so we also saw yesterday that as we increase the pore pressure, not all fractures get reactivated at the same time, and we discussed that with also with one example from Sobak and one of his students, and this shows that very clearly. As we move this circle to the left, the first point that will touch the friction line will be this purple fracture right here. So this, in terms of order of reactivation, this will be number one. This is the one that touches first. If you keep increasing the pore pressure, the next one will be this one. But the other one is already open, but then you keep increasing the pore pressure, and this fracture will become reactivated. And eventually, this might become reactivated if this is definitely the more perpendicular it is, the harder it is to reactivate, or maybe it won't reactivate at all, as we showed yesterday with one of those examples from Sobak. Okay, so this is a very important concept because it has a lot of applications in different areas. This concept of likelihood of a slip likelihood concept. So how can we use that for? Why this is an important concept? Well, we've seen applications already of the idea of critical stress fractures. So it can help us identify closer conductive fractures or fault zones. Remember that this was the concept used in the Sumatra example, the Suban field that we discussed yesterday. So this can help identify closer conductive fault zones under current stress conditions. So this is the idea of critical stress fractures. Okay, we know that we saw examples of that of this part, and we're going to use that in the exercise. The second reason is that it will help identify fractures that are more prone to slip after increasing pore pressure, which is the idea of fracture reactivation. So one case, if when these conditions remain static, like the Suban example, this is what nature gave you at that time. So some fractures will be open, some will be closed, and you're after the ones that are open. In other cases, all the fractures are closed, let's say a tight reservoir, but then you increase the pore pressure to reactivate those fractures. So this concept is exactly the same, and it's important. The slip likelihood is important also in that case. Remember, the slip likelihood is basically this parameter. And then but then there are other applications that are also extremely important. For instance, fault slip potential and induced seismicity, and this is very important. For instance, in geothermal applications, if you're going to inject water and perhaps in some areas, and maybe you hydrofrac and you increase the pressure, are you reactivating with that water, by that increased pressure, other faults? Or if you are in a process of storing wastewater after production, so are you storing near faults that are going to remain sealed forever, or you are going to create seismicity after you increase the pore pressure by storing that water there, and then and eventually creating an earthquake, which has happened, is well documented in many places, that this wastewater simply creates earthquakes that were not there before. So it's very important. And also, if you are in a reservoir that is compartmentalized, this methodology can help identify which areas can be sealing, or which faults can be sealing and which faults can be leaking. Okay. We're going in the spreadsheet, we are going to do a big simplification, and is that we're going to assume that the fractures are vertical. We're going to assume that we are in a strike and slip regime, so that we can use these Mohr circles, what is called in 2D, exactly the same representation that you have here. That's what is implemented in the spreadsheet. In reality, that this is a simplification that works only sometimes. It can give you an idea, but in reality, you may need to do consider these Mohr circles in actually considering that the relations between considering the actual three-dimensional dimensions between the fracture orientations and the uh, orientation of the different stresses. Okay, so this, you have to consider the kind of the tensor nature of this problem. But we're going to make a simplification just for the sake of the exercise, and we're going to work everything in 2D. Okay, vertical fractures. That's basically the main assumption. So this is why it's important. And now we go to the exercise. Okay. Before going to the exercise, let me show you what is the spreadsheet. Okay. So what do we have in the spreadsheet? We have here what is the input data. We have the minimum horizontal stress, and the units are psi per foot. If you want to change units, we put here a little converter to, if you want to go to other units. But here is everything here is in psi per foot. So the input data is the minimum horizontal stress, the gradient, so it's psi per foot, the maximum horizontal stress gradient, the orientation of SH max, the pore pressure, and we can see here all the ingredients that we need to calculate the likelihood, the slip likelihood. We need the coefficient of friction. We need the depth to be able to convert from the gradient to the actual minimum and maximum stresses. And what the calculator will give you is the maximum horizontal stress, the minimum horizontal stress. I mean, you input the gradient, and then with the gradient you calculate the actual values of stresses, and it will give you the pore pressure. This input here is the pore pressure gradient. Okay. So this will be the output. Another input is here is that your angles. You can input up to 10 angles. So here I put simply a list between 0, 20, 40, 60 just for this example, but you can change those. And then it will tell you for these geomechanical parameters and these orientations, it will tell you whether each of the orientations that you are using is critically stressed or not. So it's yes or no. And then it will tell you how much pore pressure you will need. If it's not critically stressed, how much you will need to reactivate it, how much pressure. And then it shows here that the relation of the friction line with the fractures in the Mohr cycle. So for instance, if we here we have this pore pressure, if we reduce the pore pressure and we make it hydrostatic, for instance, so then we move the Mohr cycle to the right, none of these fractures will be reactivated. So what it tells you here is that, okay, you need to increase pore pressure by 2,500 psi in order to be able to reactivate this fracture that is at 0. And here it will give you a plot of those numbers. Okay, this is how much extra pressure you need to apply. So you can see here easily that these two fractures, or this red point is the orientation of the maximum horizontal stress. Right here, SH max, this red point. So this tells you that these two fractures are the closest to 0. So this one at 20 degrees, you need 21 psi to be able to reactivate that. This one that is at 80, you need 2138. so this one is closer right here at 20 degrees. This is closer to being reactivated. And then it will tell you also that some fractures that are all these ones here above 120, 140, 160, they're impossible to reactivate. You won't be able to do that no matter what, because they are the angle with respect to the maximum horizontal stress is too large. Okay. So that's what the spreadsheet does, and then again I'm going to put the water pressure here in another number. I put, I don't know, 0.6, and then you start moving some fractures, and then you put 0.7, and then you move some, and then it will show you here the fractures, the orientations that are reactivated. So as you increase this one, you may get more reactivations until yeah, that's all you can do in this case. Okay. So it will show you that you can change the orientation of the maximum horizontal stress. So I don't know, we can put it here at 90 degrees. So then other set of fractures will reactivate. Other set of fractures will be above the friction line. Okay, now that we know what the spreadsheet does, let's work on the exercise. Okay, all right. Number one. For the given parameters, which fracture orientation has the highest potential to slip? So we have to introduce these parameters. So let's make sure that I have those. So we have from 0 to 180 for the angles, and then we have this is the angle maximum horizontal stress. The pore pressure is 0.45. Which is hydrostatic pressure, so it's like a column of water. The friction coefficient is 0.6. Okay, so everything seems to be fine. Okay, so this is the input data. So the first question is how much I'm sorry. Which fracture orientation has the highest potential to slip? Okay, so what we do is that we come to the spreadsheet. Oh, okay, so we come to the spreadsheet and we say, okay, which of these fracture orientations has the highest potential to slip is the one that requires the smallest pore pressure. So if you come to this plot, it will be right here at 20. So it will be 21, 21. That will be the fracture that will slip first. So okay, nice. So that will be the answer to this question 1A. Then how much extra pressure is needed to fail? Oh, okay. So it's 21, 21. We already answered that. Easy, because it's this number here. If you increase the pressure by this amount, that fracture at 20 degrees will reactivate. Then, which orientation will slip second? Oh, okay. So all we have to do is to come here and say which one has the next small value. So this was right here was 20, and then we come here and then it's 80. So if we come here to 80, so that's the one that will reactivate next. So 2,138 psi. Okay, so that's all. You plug those numbers and you answer that. So then we go to part number 2. The pore pressure gradient in the previous question is nearly hydrostatic. Okay, 0.45. Now increase the pore pressure gradient to the hydrofraclific, which is the maximum that you can pump, 0.8 psi per foot. Which orientations cannot be reactivated? So we come here to the spreadsheet and we put the pore pressure to the maximum it can go, which is 0.8. 0.8 is the minimum horizontal stress. You cannot go beyond that. So then what you see is that all these fractures will reactivate, which has all these blue ones, but then there are some that will tell you impossible. So no matter what you do, these fractures here that are right here at, 120, 140, 160, they won't get reactivated ever. So yeah, that's the answer. So we go to number 3. Now change the orientation of SH max to 130 degrees. So we come here and we put SH max instead of 45, we put 130. Okay. Assuming same pore pressure as in part 2. Okay. Which fracture orientations do not get reactivated? So now it's the opposite. You know, for one orientations, we reactivated once, some, but then those suddenly become impossible if you rotate your maximum horizontal stress. So what was possible before for different stress becomes impossible. You won't be able to reactivate that. So that's the answer to that part. So it will be 20, 40, and 60. No, which are here in the Mohr circle. And then the second part of the question is, what can you conclude about which fracture orientations get reactivated and which don't with respect to the maximum horizontal stress? And the answer there, of course, is that orientations that are around SH max, they can get reactivated. Orientations that are perpendicular to SH max, they won't get reactivated. Okay. Now we go to number 4. Assume a hydrostatic pore pressure gradient of 0.45. So, oh, okay. I'm sorry, I didn't see there is a question here. How do we get the friction coefficient? Okay, that's a good question. Sorry, I didn't see that before. I was busy explaining the exercise. The friction coefficient is something that typically gets measured in the lab from core data, and so you send your samples to a lab, and they will give you. But then typically what we have seen and what the experience is telling us is that if the coefficient is not 0.6, it will be very close to 0.6. So if you want to start with a number for loss of rocks, a good number to start with is 0.6. But I mean that if you have the ability, or if you have the resources, or if you have access to a lab that can confirm, okay, what is my friction coefficient in my area, that is something that has to be tested. Sometimes, as I said, we always have to be aware of clay content. So sometimes that the clay content can change dramatically the value of the friction coefficient. So this 0.6 can go perhaps to 0.3 to have another slope. But if you don't know anything else, and you want to start at least having an idea, starting with 0.6 is a good approximation. Okay. All right. So here we go to number 4. Number 4, assuming a hydrostatic pressure of 0.45 psi per foot, and using the same orientation as in part 1, 45 degrees. So we're going to come back here to 45 degrees. Okay, and then we're going to use 0.45 for the pore pressure. Also, assume also that the maximum horizontal stress is 1.4. Okay, so instead of 0.8, I'm sorry, no, instead of 1.1, we're going to put 1.4 for the maximum horizontal stress. Okay, so now it's, remember, it used to be 1.1. Oh, sorry. So it used to be 1.1, and this is how the Mohr circle looks with 1.1. But now we're going to increase the maximum horizontal stress to 1.4. So now it's a bigger Mohr circle. And this Mohr circle now will be closer to the friction line. So now it asks, okay, which fracture set will reactivate first? So you come here. Now for this maximum horizontal stress, you come here, and again, it will be 20 degrees in this case. That didn't change. So it's the same fracture set that you are at risk if that was a risky thing to do to reactivate. But the difference now is that, and then you go to the second part of the second questions here, part number B. How much extra pressure is needed to fail? And what you can see is that now that the rock is more anisotropic, the difference between maximum and minimum stress is larger. What is happening is that it requires less pore pressure to reactivate it. It is only 700 psi. Remember when this was 1.1, it required 2,000 psi. But now with 1.4, it's actually easier to reactivate that fracture. So the final question is, what can you conclude about the relation between reactivation pressure and stress anisotropy? So what this is telling us is that as we increase the stress anisotropy, it will be actually easier to reactivate these fractures because they are basically closer to the friction line. Okay. So you can test all these hypotheses on your own. I'm going a little bit quickly perhaps here, and then finally, if we go to go back here to 1.1, and then going back to the question from Everton. Okay, what happens if you reduce the friction coefficient to 0.4? So now, instead of the 0.6 here, that we're going to put the 0.4. Oh, okay. So now the 0.4 will bring the friction line and the Mohr circle, that will bring that closer again. So then you can go over the same exercise, but now the orientation that will be closer to reactivation will be 80 degrees. Not 20 as before. 20 will be kind of close, but it still will be 80. Okay. So this is the first part of the exercise. I don't know if you have any other question, because then we'll go to the last part of the second part of the exercise that I believe is also I think is important. Okay, if there are no questions, we'll move on to finish with the exercise. We showed this yesterday from the Sumatra example, and that in this study they took the fault orientations, and they did this kind of analysis to estimate the slip likelihood, and determine which portions of the faults were critically stressed and which were not critically stressed. So what we're going to do in this exercise is basically the very same concept that they applied here, but we're going to do it in a very simple for a very simple fault, but it's basically the same idea. See which portions of a fault can be critically stressed and which are not critically stressed. Okay, so here is that exercise, the fault slip potential. So here we have a strike and slip fault that is near to a water disposal well. Okay, remember, we then inject water, and then we are increasing the pore pressure when we do that. So what we are going to we'll try to see with this exercise is what happens when we inject that water. Are we going to create an earthquake? Okay, so these are the orientations of the fault. 135, 150, 135, 150. So we make sure that we use the right parameters here for this example. Oops. Okay, so these are the geomechanical parameters are 0.8, 1.1, 45 degrees, 0.45. Okay, and then these are the two orientations, 135 and 150. So I'll come here and type 135. So we'll put only two orientations, and then we put 150. Okay, we only have two orientations here. Okay, and then the orientation of the maximum horizontal stress is 130. So instead of 45 here, we put 130. Okay. Okay. So number one, assume the geomechanical parameters are constant across the fault. For the given parameters, which orientation has the highest potential to slip? So when we come here and see, okay, which one has the lowest number, and then what we see, okay, the one that is closer to has that requires the less pressure is this one here at 150. Okay, so these portions of the faults at 150 will be more likely to reactivate. So if you're going to create an earthquake, it will most likely come from these zones. And then it says how much extra pressure is needed to fail. So you can hear and see, okay, the extra pressure will be right here, 2,000 psi additional of pressure when you inject that water. When that happens, these orientations will reactivate. Okay. Number two, the pore pressure gradient in the previous question is nearly hydrostatic. It's close to is 0.45. Now increase the pore pressure gradient. Now you are pumping the water. Now it's 0.7. So we come here to the spreadsheet, and instead of 0.45, we put here 0.7. Okay. Which fault segment will likely generate induced seismicity? Now you are injecting the water, and then you have one point that crossed the friction line, and that point that crossed the friction line was the one that has higher chance of being reactivated, which is 150. So if you pump that amount, or if you increase the pressure for that amount, then that particular portion of the faults is likely to generate induced seismicity. Then it says here, change the orientation of SH max to 140 degrees. We're going to change that. We can hear SH max, instead of 130, we move it a little bit. We put 140. Okay. And then it says, what can you conclude about the stability of the fault in these conditions? Well, if the maximum horizontal stress is 140, then it seems that everything is stable, but man, it's very close to being reactivated. So maybe a little bit of increased pore pressure to 200 psi, which is not much, and then you are kind of very close to generated seismicity. So that will tell you why it's important to have a good understanding of these geomechanical parameters, the orientation of stresses, the orientation of your faults, because you before you work on these projects of water injection, because the generation of induced seismicity is something that I mean you need to take care of that and make sure that under your particular conditions that won't happen. If that's your goal, of course. If you want to generate the earthquakes, then it's fine. But if your goal is to avoid that, you have to have a clear understanding of the geomechanics around those faults. Now, finally, change the orientation of SH max to 45 degrees. So we go here to SH max and we put 45. Okay. Assume that the pore pressure gradient is equal to the hydrofracture limits. Now we're going to put all the pressure that we can. We're going to take that to 0.8. Okay, so that is pumping all the pressure and with this maximum horizontal stress. So, and then it says, what can you conclude about the stability of the fault for this stress orientation? And well, if you read here, it says all impossible, which means that it's for this orientation that is the maximum horizontal stress close to perpendicular, like it will be like taking this arrow and put it like this, roughly. So for that condition, that fault will be very stable, and then you can pump as much as you want. Well, and the most you will be able to pump will be up to 0.8 Otherwise, you'll create a hydraulic fracture, so you have to stop there. But still, it won't be much larger than that. And then that fault, that the whole fault will be stable. Okay, but when the maximum horizontal stress is kind of so parallel to the fault, then you have to be careful because some portions may reactivate.